So in the second part of the lecture series on sequence of real numbers, we will be discussing a few more properties of the sequences and particularly the algebra of limits. So let us start. The first result is that a convergent sequence is bounded. So in the last lecture, we ended at the point where we showed that the limit of a convergent sequence is unique. And this is the next result, which says that a convergent sequence is bounded. So let us try to see how to prove this. Suppose you take a convergent sequence and suppose that the sequence converges to a point L. So let limit n tending to infinity Sn v equal to L. Then we know that for any epsilon positive, we will be able to get a positive integer capital N, so that after the nth term, every term of the sequence will lie in the epsilon neighborhood of L. So in particular, here what we do is, instead of taking any random epsilon, we choose a value. Suppose epsilon is equal to 1. Then for epsilon equal to 1, we will be able to get a positive integer n, so that for all little n greater than equal to capital N, mod of Sn minus L is less than 1. Right? So use this inequality to check what is happening to mod of Sn. So mod of Sn can be written as mod of Sn minus L plus L. So if you use the triangle inequality, you get mod Sn is less than or equal to mod Sn minus L plus mod L. Now, if your little n is greater than equal to capital N, then mod of Sn minus L is less than 1. So what do you get finally is that for all little n greater than equal to capital N, mod Sn is less than 1 plus mod L. So you have got a bound 1 plus modulus of L for the modulus of the terms of the sequence Sn, but after a certain term. That is, starting from capital N onwards, every term has the property that mod Sn is less than 1 plus mod L. But you want to show that the sequence is bounded, so you want to get a bound for all the terms of the sequences. So what you notice is that finitely many terms are left out from this. What are the terms which are left out? They are precisely mod S1, mod S2, mod S3, etc. till mod Sn minus 1. So look at these numbers. These are non-negative numbers. Some may be 0, some may be positive. It doesn't matter. So look at all these numbers and look at 1 plus mod L, which was the bound which you got here. So then you are getting capital N many non-negative numbers, and at least one of them is positive. 1 plus mod L is positive. Whatever be the value of L, it doesn't matter, right? So therefore you have, if you look at the maximum of these capital N numbers, that will be a positive number. So capital K is going to be a positive number, which is equal to the maximum of all of them. Now, since capital K is the maximum of all of them, so mod S1 is less than or equal to K, mod S2 is less than or equal to K, and so on. Mod Sn minus 1 is also less than or equal to K. And what happens to mod S little n when n is greater than or equal to capital N? Then that number we have seen is less than 1 plus mod L, and 1 plus mod L will be less than or equal to K. So therefore, for every little n greater than equal to capital N also, mod Sn will be less than or equal to K. So what have you got by this choice is that mod Sn is less than or equal to K for all little n positive integers. So every term of the sequence will lie in the closed interval minus capital K to plus capital K. So its range is a bounded set, and hence the sequence is a bounded sequence. Fine. So we have proved that a convergent sequence is bounded, and the converse of this statement is not true in general. So to see that, what we will do is we will look at an example. We have seen this type of example in the previous lecture also. Just look at Sn is equal to -1 to the power n for all n in n. Then what does this sequence look like? If you take n equal to 1, then it will be -1. If you take n is equal to 2, it will be 1. If you take n to be any odd positive integer, it will be -1 because it is -1 to the power odd. So that will give you -1. And if you take n to be any even positive integer, then Sn is going to be 1. So it is an oscillatory sequence oscillating from -1 to 1 to -1 to 1 and so on. So this sequence is clearly not uh, a convergent sequence. We saw a similar sequence in the last lecture. It is obvious that it cannot converge to a limit, right? And what do you know about this sequence further is that the range of the sequence is just the set containing two points -1 and 1, because these are the two values which the sequence is taking. Therefore, Sn is clearly a bounded sequence. It is going to lie between the closed interval -1 to 1, right? So Sn is a bounded sequence. It is clearly not a convergent sequence. So if you have a bounded sequence, it may not be convergent. But if your sequence is a convergent sequence, then it is necessarily a bounded sequence. Okay. So the next result is the same sign theorem. So this is again a very important theorem. So what does this say? It says that suppose limit n tending to infinity an is equal to a where a is not 0. So a is either positive or negative. Then you will be able to get a positive integer capital N, so that after the capital nth term, an and a will have the same sign. So that means what? That if a is positive, then after a certain term, every term of the sequence will be positive. If a is negative, then after a certain term, every term of the sequence will be negative. So always you notice, in the last class also I had stressed on this point, then that when you are talking about the behavior of a sequence, you are looking at the tail of the sequence, meaning you are not bothered about what is happening to the first few finitely many terms of the sequence. They may behave randomly, but if you have a convergence and things like that, then you will expect that after a certain stage, the sequence will have a certain nice behavior depending on the condition put on the sequence. So here we are saying that the sequence is convergent, and not only it is convergent, its limit is non-zero. So if its limit is non-zero, then it is either positive or negative. So you are saying that after a certain term, all the terms of the sequence will be of the same sign as that of its limit. So this is a beautiful result and obvious terminology, same sign theorem. So in particular, after a certain stage, an can never be 0. If the limit is non-zero, then you will be able to find a certain term of the sequence after which none of the terms will be 0. So let us try to prove this. Proof is very interesting, and we will be using this type of proof later on also. So first of all, we know that a is non-zero. So instead of epsilon, you take modulus of a divided by 2. Since a is non-zero, modulus of a is a positive number. So modulus of a divided by 2 is also a positive number. For this value of epsilon, since limit n tending to infinity an is equal to a, this is a given. Therefore, you will be able to get a positive integer capital N, so that for all little n greater than equal to capital N, modulus of an minus a will be less than mod a divided by 2, right? That is the definition of the existence of limit, that for any epsilon you should be able to do this. So in particular, for epsilon equal to mod a divided by 2, you are going to get a capital N so that this inequality holds for all little n greater than equal to capital N. Now you stare at this inequality. What you do first of all is that you use the equivalent uh, inequalities which imply this. Remember in the lecture some long time back, when I had talked about modulus of numbers, I had proved certain inequalities. One of the inequalities is this, that if you have mod n minus a less than mod a divided by 2, that is the same as, actually it is equivalent to the condition that minus mod a divided by 2 is less than an minus a is less than mod a divided by 2. So people who have forgotten these things are advised to go back to those lectures. I think it is a lecture on real numbers. I don't perfectly remember, but in one of the previous lectures we have talked about inequalities. You should go back and just see those lectures. Okay, so we have this inequality, set of inequalities, which is the same as this inequality. Now what I'm doing is I'm doing a very simple thing. I'm adding a throughout. So I get a minus modulus a divided by 2 is less than an is less than a plus mod a by 2. And this is true for all little n greater than equal to capital N. Very good. Now you take the two cases. First you suppose that a is positive. Then what does this mean? If a is positive, then modulus of a is equal to a. So a minus a by 2 is just a by 2. So you will get a by 2 less than an less than, and what does this become? A plus a by 2, so 3a by 2. That is true for all little n greater than equal to capital N. Now a is positive means a by 2 is positive. So therefore an is greater than 0 for all little n greater than equal to capital N. Is it clear? 0 is less than a by 2 less than an less than 3a by 2. So an is going to be greater than 0, and that is true for all little n greater than equal to capital N. So an has the same sign as a after the capital Nth term. Similarly, if you take a less than 0, then what will happen here in this inequality is that modulus of a now becomes minus a. So it becomes a minus minus a. So it becomes 3a by 2. That is less than an. That is less than a by 2. Right? A minus a by 2. So that becomes a by 2 for all little n greater than equal to capital N. So now what is happening is, don't get confused by this inequality. Remember that a is less than 0, so this is perfectly all right. And now a by 2 is less than 0 because a is less than 0. So what have you got? You have got that an is less than 0 for all n greater than equal to capital N. So an has the same sign as a after the capital Nth term. So you have proved the theorem, and not only that, you are observing that since it has the same sign as its limit after a certain term, so the an can never be 0 for all n greater than equal to this given term capital N. So an is a non-zero number after the capital Nth term of the sequence. Okay, so we have this result. Now let us look at a few consequences of this. So we look at it from the other side. Suppose that limit n tending to infinity Sn is equal to L and all the Sn's are greater than equal to 0. That is, you have a sequence whose terms are lying on the positive side, or rather the non-negative side of the real axis. That is, it may be 0 somewhere, but it is never going to be negative. So Sn is greater than equal to 0 for all n. Then you want to claim that L is greater than equal to 0. How will you prove this? This is just a follow-up of the previous theorem, that if L is not greater than equal to 0, then L has to be less than 0. But if L is less than 0, then after a certain term, all the terms of the sequence have to be negative, which is a contradiction. That is all. So we have written down carefully here that if possible let L be less than 0, then if you take epsilon to be equal to minus L by 2, you will get the same proof. See, there is nothing extraordinary here. Modulus of Sn minus L is less than minus of L by 2 because now it is positive after a certain term. So for all little n greater than equal to uh, capital N, I think I've gone to a different page. So for all little n greater than equal to capital N, you have modulus of Sn minus L is less than minus L by 2. This is your epsilon. So again, as you did in the previous thing, you just expand it. So if you expand this, this is what you had got for negative thing, right? So I'm just copying that here. So we are going to get 3L divided by 2 is less than Sn is less than L by 2. So that means that Sn has to be negative after the capital Nth term, which is a contradiction because we have assumed that Sn is greater than equal to 0 for all little n for all positive integers n. So if you have a sequence consisting of non-negative terms and if the sequence converges, then its limit also has to be non-negative. It has to be greater than equal to 0. So similar result is when you take less than or equal to 0. That is, suppose you have a convergent sequence and it all of whose terms are non-positive. That is, all of them lie on the non-positive axis, that is on the left hand side of 0 or 0 on the real axis. So then the limit will also be non-positive. It will be less than or equal to 0. Argument is the same because if L was not less than equal to 0, then L would be greater than 0. But if L is greater than 0, then by same sign theorem, after a certain term, all the Sn should be positive, and that is a contradiction to our assumption. So we have written down carefully here that if L is greater than 0, you take epsilon to be L by 2, then you will be able to get a capital capital N positive integers, so that after the capital Nth term, if you look at modulus of Sn minus L, that will be less than epsilon by 2, which will imply that Sn will be positive, which is a contradiction to our hypothesis on the terms of the sequence. So if all the terms of the sequence are less than or equal to 0, and if it converges, then the limit is also less than or equal to 0. Straightforward. Okay, so if you remember the same sign theorem, then these things are not going to be difficult. Okay, next what we will do is we will do some algebra of limits. You may think that why do we bother about this? It is enough to know the results, but I insist upon it because this will help you to get a working knowledge of sequences. That is, you will know how to handle the sequences which you encounter. So it is better to do these exercises. Advice as usual is that mathematics is not learnt by just hearing or reading. You have to do mathematics. So whatever we are discussing, everything you should be writing down in your notebook or something on your own, so that you get the knowledge fixed in your mind. Okay, so let us just start with the first one. That suppose you have uh, two convergent sequences, and suppose limit n tending to infinity an is equal to a and limit n tending to infinity bn is equal to b. Then if you add term by term, that is, construct a new sequence whose nth term is an plus bn, then this new sequence will also be convergent and it will converge to a plus b, right? So let us see how to prove this. Proof is very straightforward. It is just a manipulation of the definition of convergence of a sequence. So you should be very careful about it, how to do it without mistakes. So you want to show such a limit is such a result is true. So you, how do you do that? You choose any epsilon greater than 0 and then try to find a suitable capital N positive integer so that the required inequality will be true. So how will we do that, proceed towards it? Is that we have something in hand. We know this limit exists and this limit exists. So using the fact that these two limits exist, we will get that capital N. So let us see. Suppose we have epsilon greater than 0, then since limit n tending to infinity a n is equal to a, I will be able to get a positive integer capital N1, so that modulus of a n minus a is less than epsilon by 2 for all n greater than equal to n1. So remember the definition. What did it say was that for any epsilon you should be able to get a positive integer n. So what we do is that instead of we start with an epsilon greater than 0, and instead of trying to find a term after which modulus of a n minus a is less than epsilon, we try to find a term after which modulus of a n minus a is less than epsilon by 2. The reason behind this is actually just simple aesthetics. There will be some addition in the end, so that this epsilon by 2 and the other epsilon by 2 which we get added will give you epsilon, and it is satisfactory to get an epsilon at the end. So that is the only reason you are taking epsilon by 2. If you had chosen an epsilon here, I'm spending some time on this because this is crucial, that if you had just chosen mod a n minus a less than epsilon, and again here also same type of thing, then when you had added, you will see there is some sort of addition going on. So then you would have got 2 epsilon. So since epsilon greater than 0 is arbitrary, for any epsilon greater than 0 you should be able to get. If you get for any 2 epsilon, where epsilon is arbitrary, it is perfectly all right, because whatever, suppose I want to show it for epsilon is equal to 0.25, and I show it for say, no, not a nice choice because now I have to divide by 2. So suppose I want to show it for epsilon is equal to 0.5, and I start with epsilon equal to 0.25 and then take twice of that, I will get a 0.5 here, right? So uh, since epsilon is arbitrary, so 2 epsilon is also arbitrary, so it would not have mattered. So you don't have to really rigorously remember that I have to take a divided by 2 here, so that when I add I get a neat thing, I get an epsilon. What you can do is you can just simply write down your definitions for less than epsilons, and then in the final thing you'll get a 2 epsilon. But since epsilon is arbitrary, 2 epsilon is also arbitrary, so your result will follow. It doesn't really matter. The only thing is that when you are multiplying that arbitrary epsilon positive by a number which will be 2 here, should be a positive number. That is, if you take any epsilon greater than 0 and prove that final inequality, whatever you want to get, is less than some k times epsilon, k randomly you'll get via some calculations. If that k is positive, that is sufficient for your proof. That is as arbitrary as epsilon, positive numbers. So I think you are able to understand a little bit here as to what I'm trying to say, and it will become clearer as we go on. So since in this is the first time we are doing these type of manipulations, so we have been slightly careful, and instead of epsilon, for epsilon by 2, I'm saying that since limit n tending to infinity a n is equal to a, I will be able to get a capital N 1th term, so that after that term, mod a n minus a is less than epsilon by 2. Similarly, for the same epsilon by 2, I will be able to get n 2th term, so a positive integer n2, so that for all n greater than equal to n2, mod bn minus b is less than epsilon by 2. Notice that a priori, that is beforehand, you cannot assume that these n1 n2 are the same. All you know is that limit n tending to infinity a n is going to a, and limit n tending to infinity b n is equal to b. So that means that after a certain term this inequality should hold, and for the sequence a n, and after a certain term this inequality should hold for the sequence b n. But that doesn't mean that this n1 or this which term will be independent of the sequence a n and b n. That is not true. Depending on the sequence an, you will get n1, Depending on the sequence Bn, you will get N2. So now how to manage it? The management is the following, that after capital N1, for every term, this inequality is true, and for after N2, for every term, this inequality is true. So if you take the maximum of N1 and N2, then both the inequalities will be true after the capital Nth term. So starting with the definition of the limits, you will get an N1 and an N2, but infinitely many terms are after capital N1 and capital N2. So just take the maximum of N1 and N2. Then after that capital Nth term, both these inequalities will hold together. That is, mod an minus a will be less than epsilon by 2, as well as mod bn minus b will be less than epsilon by 2 for all little n greater than equal to capital N. Now what you do is you use some things regarding inequality which you have learned. In particular, here we are going to use triangle inequality. So what do you have to check is that limit n tending to infinity an plus bn is equal to a plus b. So what we are doing is we are writing down a random term of the sequence, nth term, so that is an plus bn minus a plus b, and take the modulus of that. So by you can write it as mod of an minus a plus bn minus b, and then use the triangle inequality. You will get this is less than or equal to mod an minus a plus mod bn minus b. So till this portion, it is true for any n, right? Just by triangle inequality. Now what you do is that if you take your little n to be greater than equal to capital N, then modulus of an minus a is less than epsilon by 2, and modulus of bn minus b is also less than epsilon by 2. So modulus of an minus a plus modulus of bn minus b will be less than epsilon by 2 plus epsilon by 2. So that is going to be equal to epsilon. So what do you get by your transitivity property? That modulus of an plus bn minus a plus b is less than epsilon for all little n greater than equal to capital N. So given any epsilon positive, you were able to choose a positive integer capital N so that the required inequality holds. Epsilon was arbitrary, and hence you can claim that limit n tending to infinity an plus bn is equal to a plus b. Proof is not difficult, but there is a idea here, new idea. So please keep this in mind, that if you have finitely many things like this, then you can just take the maximum so that all the inequalities hold after a certain term. This was one of the ideas which we had here. That is the basic thing. Okay. So this is the first proof, that sum of the limits is the limit of the sum, right? Sum of the limits is the limit of the sum. Okay. Next result is that suppose you have a convergent sequence an, and suppose limit n tending to infinity an is equal to a. Then if you construct a new sequence which is just multiplying term by term each term of this sequence by a real number c, then you'll get a new sequence CAN. Then CAN will also converge, and in fact limit n tending to infinity CAN is equal to CA. So let us go through the proof of this. How to do it? First of all, we will do the case when c is equal to 0, because that is a special case. If c is equal to 0, then what happens to CAN? CAN is just equal to 0. Therefore, the sequence CAN is the constant sequence 0, right? So we have seen that the limit of this is 0. That is, it is a null sequence. So CAN all will become 0, and the limit n tending to infinity of this will be equal to 0 into A, which is equal to 0. So for C equal to 0, at least the result is true. Next, what we do, that we take the case when C is non-zero and take any epsilon greater than 0. We have to find a capital N so that a certain inequality holds. We will use the fact that limit n tending to infinity an is equal to a here. So whatever is given, we use that to prove what we have to. So since limit n tending to infinity an is equal to a, for this epsilon greater than 0, you just look at the positive number epsilon divided by modulus of c. Now this is a positive number because c is not 0. So for epsilon divided by modulus of c, there is a positive integer n, so that for all little n greater than equal to capital N, modulus of an minus a is less than epsilon divided by mod c, because this limit exists. Okay, so what does that mean? Just multiply by mod c. uh, this inequality changes to what? If you multiply by mod c here, then you get mod c into mod an minus a, but that is just equal to modulus of can minus ca, and that is less than mod c into epsilon divided by mod c. So mod c cancels out, you are left out with epsilon. So for any little n greater than equal to capital N, you did not have to manipulate the capital N, it remains the same one. For any little n greater than equal to capital N, you have got that mod can minus ca is less than epsilon. And since epsilon was arbitrary, this proves that the limit n tending to infinity can is exactly equal to ca. Right? So the next result in algebra of limits is about products. So again, suppose that limit n tending to infinity an is equal to a, and limit n tending to infinity bn is equal to b. Then we will show that limit n tending to infinity an into bn is equal to ab. So how do we do that? Uh, you could have started doing the proof on your own and encountered some problem somewhere and then gone back and corrected that. But since it is I who is lecturing and you who are listening, so I have some idea as to how to proceed so that I don't encounter any problems. So therefore I am going to start with the fact that since an is a convergent sequence, it is a bounded sequence. Why did I suddenly start with this? You will understand as we go through the proof. The reason is that I had to start with something in using my instinct, and then I ran into some trouble, and then I had to go back and correct it. That is the way the proofs are done. But after one gets the idea of the proof, then one writes it down neatly, so that sometimes it is very surprising to see that suddenly why are we bothering about it. We did not bother about this fact in the previous two results, but here it becomes necessary. And why is it necessary will be clear. So let us see. So first of all, an is a convergent sequence, so it is a bounded sequence. So I will be able to get a positive number, need not be integer, but I think I would take an integer. So suppose I take a I will be able to get a positive integer, so that mod an is less than m1 for all n. Because it is a bounded sequence, I will be able to get this. Now you look at m1 and modulus of b. Okay, it's not necessary maybe that this is integer. Suppose I take any positive real number. So if you look at m1 and mod b, see, an is converging to a and bn is converging to b. There is nothing known about what is the value of a and b. So a could be 0, b could be 0, we don't know. So we just look at the maximum of m1 and modulus of b. Then what is the trick so called involved here is that m1 was a positive number. So since an is a bounded sequence, mod an is less than m1, this we will get for a positive number m1. So if I look at the maximum of m1 and mod b, that will be a positive number. So m is greater than 0, right? Even if mod b is 0, we don't care. Okay, now suppose I take any epsilon greater than 0. Then again, limit n tending to infinity an is a and limit n tending to infinity bn is b, means that there will be a positive integer n1, so that for all n greater than equal to n1, modulus of an minus a is less than epsilon divided by 2m. This is also, I have done some back calculation, so I know what I should put here. That is the only reason. Okay. So now this is okay because epsilon is positive and m is a positive number. So instead of epsilon, I am looking at the arbitrary positive number epsilon divided by 2m. For this number also, I will be able to get a n1 positive integer, so that after the n1th term, mod an minus a is less than epsilon by 2m. Similarly, I will be able to get a positive integer n2, so that after the n2th term, mod bn minus b will be less than epsilon divided by 2m. So now you use the same type of trick. You want that these two should happen at the same time. So what have you got? You've got that after a certain n1, this inequality is true. After some other n2, this inequality is true. You want both these inequalities to be true after a fixed uh, term. So you will take the maximum of n1 and n2. So this will also be true and this will also be true. So that is what we do. So you take n to be the maximum of n1, n2, then modulus of an minus a is less than epsilon by 2m, as well as modulus of bn minus b is less than epsilon by 2m for all n greater than equal to n. So at the same, after the same term, both these inequalities are true. That is going to be helpful for us. So now let us see, what are we going to do? Take any little n greater than equal to capital N. In the first few things we will not require it. It is only here that we will need. Okay. So look at mod of an bn minus ab. We have to do some algebra here. So instead of bn, suppose I write an into bn minus b. So I have introduced one term minus of a and b here. So I have to also write a plus a and b, so that that cancels out. So I have done that. So I'll get a plus a and b minus ab. So from this I take the b common. So you get this number in the modulus. So therefore an bn minus ab is equal to modulus of an times bn minus b plus b times an minus a. I hope it is all right. A and b is cancelling out. Now what you do is you treat this as one number and treat this as another number. Use the triangle inequality first. Then you will get less than or equal to modulus of an times bn minus b. That is not written here. Okay. So modulus of an times bn minus b plus modulus of b times an minus a. But that is the same as mod of an times mod bn minus b plus mod b times mod an minus a. So there is a very slight step jumping here. You use the triangle inequality and then you use the fact that mod of xy is equal to mod x into mod y. So using those two facts, we have got this. Okay. Now what do we know? We know that an is a bounded sequence, remember. So mod an is less than m1, but m1 is less than or equal to capital M, because capital M is the maximum of m1 and mod b. So mod an is less than m for all n positive integers. So use that fact. So instead of mod an, you write down capital M and then write down mod bn minus b as it is. Again, here you have mod b. So what did you know about mod b? Capital M is the maximum of M1 and mod B. So mod B is also less than or equal to capital M. So therefore, if you replace mod B by M, again the inequality is increasing or at least not decreasing. So you get a less than or equal to here M times mod An minus A. It is clear. So here also you got this by I've explained it already, and here also replacing mod b by m, you get this. Now what you do is use this fact. So till this portion, you did not require that n be greater than equal to capital N. All this was true for every little n. But now, if you take n to be greater than equal to capital N, what do you get? M times epsilon by 2m. Mod an minus a is less than epsilon by 2m. So this becomes less than epsilon by 2m plus capital M into again epsilon by 2m. So what will you do now? Cancel out m, because m is a positive number, right? That was the crucial thing actually. So m is a positive number, so you cancel it out, you get epsilon by 2 plus epsilon by 2, so that is equal to epsilon. Notice that in this whole inequality, there is a strict inequality here, so the total effect is a strict inequality. So therefore, for all little n greater than equal to capital N, you are able to write down that mod an minus bn minus ab is less than epsilon. And this is true for any epsilon greater than 0. You had started with that, where is it? For any epsilon greater than 0, you started doing your work and you found a capital N so that this inequality holds. So therefore, the limit exists and is equal to whatever you wanted, that is product of the limits is the limit of the products. Limit n tending to infinity an into bn is equal to ab. Very good. So we have done some multiplication, scalar multiplication, addition. So as expected, there should be some division also. So what will happen there? Suppose you have a convergent sequence, limit n tending to infinity an is equal to a, and here you need a extra condition that suppose a is not 0. Then you can say that limit n tending to infinity 1 by an is equal to 1 by a. So any cautious student will say that I am assuming a non-zero, so 1 by a makes sense. But if the limit is non-zero, doesn't necessarily mean that each of these terms will be non-zero. So what do you mean by this 1 by an? Some of the an could be 0. So let us look at the proof, and you will be able to understand what I'm trying to say here. Actually, we learned this some time back in today's lecture itself, that if the limit of the sequence is non-zero, there will be a term after which the terms of the sequence will be non-zero. So when I am writing limit n tending to infinity 1 by an, I mean that I am leaving out the first few finitely many terms where there could be some zeros. The sequence is considered after the term where all the terms of the sequences are non-zero. So that is the meaning of this. We don't bother to write down that in details, but since we have already got the idea about such a thing, we understand what is the what this expression means here. Okay, so let us see how will we do that. This is slightly non-trivial because we need some small tricks. So first of all, a is non-zero and limit n tending to infinity an is equal to a. So you look at the number modulus a divided by 2. This is a positive number, and you will be able to get a positive integer capital M1, so that modulus of an minus a is less than modulus of a divided by 2. Right? Now you look at this inequality. This I have done again long time back, I think during the when I was discussing real numbers. If you have forgotten, I will insist lot that please go back and look at that particular lecture. But even if you don't want to bother about it right now, you just see what is happening here. You write down mod a. So mod a can be written as a minus an plus an. So by triangle inequality, you will get mod of a is less than mod an minus a plus mod n, right? In fact, less than or equal to, so you can take the an on the right hand side and you will get mod a minus an is less than or equal to mod an minus a. I think I should have written a less than equal to here, but it doesn't matter in the final thing, even though. So we will get this inequality just by triangle inequality. Write a as a minus an plus an. Then this use triangle inequality, you will get mod of a is less than mod of a minus an plus mod an, and then take the mod an on the left hand side, sorry. So you will get this inequality. And what does this mean? This means that if you take mod an on the right and this on the left, you will get mod an. So I should have written less than or equal to here. So I will get a less than or equal to here also. Mod an is greater than or equal to mod a minus mod an minus a. I think that is okay, right? You just take this one on this side, on the left side, and take mod an on the right side. So you get this with a less than or equal to. Okay. But what do you know about mod a n minus a? That is less than mod a by 2. So if you multiply by minus, then minus 1, then what do you get? You get minus of modulus a n minus a is greater than minus of mod a by 2. So you will get this number will become greater than mod a minus mod a by 2. So you are left out with mod a by 2. I hope I'm clear. You have this, and that will happen only after the m1th term, because this inequality is true for all little n greater than equal to capital M1. So this uh, simple calculation tells you that mod an is going to be greater than, see, there will be a less than or equal to here, because there will be a less than or equal to here, but here it is strictly greater than because of this. So the total effect is that it is going to be strictly greater than. Even though there is a typo here, the final thing is that mod an is greater than mod a by 2 for all n greater than equal to m1, because mod a minus mod an minus a is greater than mod a minus mod a by 2 from here. I think it is okay. So in particular, an is not 0, that you see, for all n greater than equal to m1, because mod an is greater than mod a by 2 means, if you look at that mod a by 2 neighborhood of 0, all the ans are outside that, so it cannot be 0. I think it is okay. This is strictly greater than 0 and so on. Okay. Now suppose you take any epsilon greater than 0, arbitrary. Then again, limit n tending to infinity an is equal to a means that instead of epsilon, if I look at the number modulus of a squared epsilon divided by 2, then for this number also, I will be able to get a positive integer m2, so that after the m2th term, mod an minus a will be less than mod a squared epsilon by 2, right? This is also true. So why are we randomly choosing these type of things? Again, I want to just explain so that you understand how things work. There is a back calculation involved. We should have started with 1 by an minus 1 by a, looked at the modulus of that and tried to estimate it. And actually people did that. And while estimating, one discovered that if we choose such strange looking numbers, then that will help. So that is what has been observed, and we are doing it in the other direction instead of going through the back calculation. Okay, so I hope I am making it clear for you that first of all we have observed this thing, and secondly, for any epsilon greater than 0, obviously since limit n tending to infinity an is a, for any for the number mod a squared epsilon by 2, also we will be able to get a positive integer m2, so that after the m2th term, this inequality will hold. So this inequality is holding after the m1th term, this inequality is holding after the m2th term. That is not a big deal now for us. We have understood that if we want everything to hold at the same time, then we will just take the maximum of m1 and m2. So after that maximum term, everything, whatever is suitable for us, will hold. So capital N we have taken to be the maximum of M1 and N2. Now I look at little n greater than equal to capital N. Then what happens? So what I was saying, this is my first step actually when I start to write the proof. And then I see that what I need, I modify things accordingly and get the final result. So I write down 1 by an minus 1 by a and take the modulus of that. So what is that? This is just simple subtraction here. So this is an minus a divided by a into an modulus, because there is a modulus here. Okay. Now see what is happening. There is a mod a in the denominator, and there is a mod an in the denominator. What do we know about mod an? We know that mod an is greater than mod a divided by 2 for all n greater than equal to capital N, because capital N was maximum of m1 and m2. So for n greater than equal to capital N, this inequality holds. So what does that mean? That 1 by modulus of an will be less than 2 divided by modulus of a. So I am going to use that fact here. So see, the numerator we have kept as it is. There is a modulus a in the denominator, that also we have kept as it is, and the modulus an in the denominator we have replaced by mod a divided by 2, so that the terms become larger, right? Because 1 by mod a is less than 2 by mod a. 1 by mod an is less than 2 by mod a for n greater than equal to capital N. So we have got this one. Now you see, what you do is you look at 2 by mod a square. You leave that as it is and look at mod an minus a. So what do we know about mod an minus a? Mod an minus a is less than mod a squared into epsilon divided by 2 for all n greater than equal to capital N. N is the maximum again of both these. So instead of mod n minus a, if we substitute mod a squared epsilon divided by 2, the number will become larger. So that is what we are doing here. Now you do some simple cancellations. Mod a squared will cancel out, 2 will cancel out, you will just be left out with epsilon. So what have you done? You chose any epsilon greater than 0, and doing some manipulations you saw that you will be able to get a capital N positive integer, so that for every little n greater than equal to capital N, modulus of 1 by an minus 1 by a is less than epsilon. So you have proved that limit n tending to infinity 1 by an is equal to 1 by a. Okay, so hopefully this is all right. Next, we will do some simple results. The first one is that suppose I take two convergent sequences, limit n tending to infinity Sn is equal to S and limit n tending to infinity Tn is equal to T. And suppose that Sn is less than or equal to Tn for all n. So you have two sequences, Sn and Tn. Sn is converging to S, Tn is converging to T, and at each term you see that Sn is less than or equal to Tn. Then what you want to say is that the limits will also satisfy the property S is less than or equal to T. Proof is very straightforward now. You have done the hard work. You first notice that what is limit n tending to infinity Sn minus Tn? This is equal to limit n tending to infinity Sn plus minus Tn, right? So that is limit n tending to infinity Sn plus limit n tending to infinity minus Tn. But limit n tending to infinity minus Tn is equal to minus of limit n tending to infinity Tn. So finally, what do you get? That limit n tending to infinity Sn minus Tn is equal to limit n tending to infinity Sn minus limit n tending to infinity Tn. So that is, you get S minus T. Very good. Next thing you notice that Sn minus Tn is always less than or equal to 0, because Sn is less than or equal to Tn. So Sn minus Tn, this sequence will be a non-positive sequence. So its limit also has to be non-positive. We saw some time back today. So therefore, S minus T has to be less than or equal to 0, which means that S is less than or equal to T. So if you have two convergent sequences like this, and if term by term Sn is less than or equal to Tn, then the limit will also satisfy the same inequality S less than or equal to T. Okay. Even before this, here also, if Sn is strictly less than Tn, then also you can only conclude that S is less than or equal to T. It may not be true that if Sn is strictly less than Tn, then S will be strictly less than T. That is not true. A very simple example is that you take Sn to be equal to 1 by n, right? That particular limit. So limit n tending to infinity 1 by n is equal to 0. So S is 0. Okay. And instead of Tn, you take 1 by n minus 1 for all positive integers greater than 1. So what am I trying to say is that Sn is the sequence 1 half, oh sorry, I wanted the opposite way. So let us do the opposite thing. Suppose Sn is the sequence half, 1/3, 1/4 and so on. Forget about the 1. And suppose Tn is the sequence 1, half, 1/3 and so on. So what is happening is that here the first term is half and here the first term is 1. So it is strictly less than, right? So you have this half, 1/3, 1/4 and so on. That is your sequence Sn. And Tn is 1, half, 1/3, 1/4 so on. So at each term level, Sn is going to be less than Tn. But what is the limit of n tending to infinity 1 by n? That is 0, and that is true for Sn as well as Tn. If you keep the first term 1 in the sequence or not, it doesn't really matter. If you look at the sequence 1, half, 1/3, etc., that also converges to 0, and the sequence half, 1/3, 1/4, etc., that also converges to 0. So it is possible that Sn is strictly less than Tn for all n, but S will be less than T. Sorry, S will be less than or equal to T. It may not be necessary that S is less than T. S could be equal to T also. That is what I gave an example of. So you have to remember that. And another caveat means warning. So let us look at this. This is also very important. What I want to say is that it is possible to have two non-convergent sequences, xn and yn, so that their sum is convergent. This is an extremely necessary thing to realize, and the proof for to understand this, what you really require is an example of two non-convergent sequences. When you add term by term, you get a convergent sequence, and this is again trivial. You just take xn to be -1 to the power n. So what does the sequence xn look like? It looks like -1, comma 1, -1, comma 1, -1, comma 1 and so on. And take yn to be equal to -1 to the power n plus 1. So how will it look like? It will look like 1 comma -1, 1 comma -1, 1 comma -1 and so on. So this is an oscillatory sequence. This is also an oscillatory sequence. But if you add term by term, what will happen? Wherever you have xn equal to -1, yn is equal to 1. So addition is going to be 0. Wherever you have xn is equal to 1, yn is -1. So the addition is going to be 0. So xn plus yn is going to be the constant sequence 0. So xn plus yn is a null sequence, converges to 0. So you have two non-convergent sequences, and if you add them, then you get a convergent sequence. It is possible. So you should keep this in mind. Next result about modulus of a sequence. This is crucial, and let us do this, and this is going to be the last arguments which we discussed today. First one is that if limit n tending to infinity Sn is equal to S, then limit n tending to infinity modulus of Sn will be equal to modulus S. This is a very straightforward result, provided you remember this inequality. So you see, the inequalities are playing a fantastically important role, and anybody who has missed it, again I'm saying the same thing, go back and look at that lecture. That is extremely important. This was proved for any two real numbers. So what is the inequality? That modulus of modulus Sn minus modulus S is less than or equal to modulus of Sn minus S. This is true for all positive integers n. We had taken maybe a and b, any two real numbers. For that, this inequality was shown to be shown to hold. So in particular, here we are taking the nth term of the sequence, any nth term of the sequence, and the limit of the sequence, and we see that this inequality will hold. Now this is going to help us. Take any epsilon greater than 0. Then we know that limit n tending to infinity Sn is equal to S. So I will be able to get a positive integer n, so that modulus of Sn minus S is less than epsilon for all n greater than equal to capital N. Now you see, this is just trivial. This one is already less than epsilon, so this one will be less than epsilon. That is all we are saying. So therefore, for every little n greater than equal to capital N, modulus of mod Sn minus mod S is less than epsilon. So what does that prove? For any epsilon greater than 0, you were able to get a positive integer capital N, so that after the nth, capital Nth term, modulus of mod Sn minus mod S was less than epsilon. Hence, limit n tending to infinity mod Sn is equal to mod S. Correct? Straightforward. Again, the converse is not true. And example is a very standard one. You again look at that oscillating sequence -1 to the power n. You can write several examples, but in literature this has become almost biblical, so we just write this one. But you could write many other examples also, as is clear. So just look at the sequence which is going -1 1 -1 1 and so on. So that is an oscillatory sequence, and its general term is written as Sn is equal to -1 to the power n, where n is a positive integer. If you take the modulus of this, then what do you get? You just get 1 everywhere. So you get the constant sequence 1. So the limit is 1. So uh, mod of Sn is a convergent sequence, whereas Sn is not a convergent sequence. So the converse is not true. If a sequence is convergent, the modulus of that sequence will also be convergent, and not only that, it will converge to the modulus of the limit. That you have proved, right? But if you have a sequence whose modulus converges, it is not necessary that the original sequence will converge. Okay, this you saw now. But there is a special case which is going to be extremely important for us, that if you have a sequence modulus of which is a null sequence, that is, it converges to 0, then the original sequence will also converge to 0. This is a beautiful thing, and this we will use many times. So how are you going to do it? The proof is by starting with any random epsilon greater than 0, and you want to find out a capital N so that things happen. Okay, so first of all, notice that limit n tending to infinity mod Sn is equal to 0. This is a given. So there is a positive integer capital N, so that modulus of mod Sn minus 0 is less than epsilon for all little n. I'm sorry. Yeah, actually this is not true. This is a typo. This is not for all n belonging to capital N. This is for all n greater than equal to capital N. Since limit n tending to infinity mod Sn is equal to 0, so for any epsilon greater than 0, there is a positive integer n, so that for all n greater than equal to capital N, modulus of mod Sn minus 0 will be less than epsilon. But what is this number? Mod Sn minus 0 is just mod Sn. Mod Sn is a positive number, or at least a non-negative number. So modulus of modulus Sn is just mod Sn, and that is equal to mod Sn minus 0. So what have you got? You have got that mod Sn minus 0 is less than epsilon for all little n greater than equal to capital N. Please take care. This is not true. For all n greater than equal to capital N. So for any epsilon greater than 0, you are able to get a capital N, so that modulus Sn minus 0 is less than epsilon after the capital Nth term. So therefore, limit n tending to infinity, Sn is equal to 0. I hope this is okay. And this particular lecture is a very important lecture in the sense that we have proved many important results. In the next lecture, we will be proving the sandwich theorem or squeeze theorem, as it is called, and using it we will compute several limits. So please keep on doing work on your own, otherwise you will feel lost. We stop here.